to be kind of coming in pretty slowly. Was there some other homework or something due today?
No, for me.
Okay. Morning. So, how was this paper? This is sort of related to the exokernel paper, right? And I think some of you complained that they didn't refer to the exokernel paper. It's possible because they were published at the same time, right? In the same conference, right? So you would argue that they should have known, but I mean, when the paper got accepted, all these people chat with each other, so it's not like they're working in the dark completely, but they only have the previous draft, right? You don't want to expose all your cards to your competitors, really, right? So you see their HeartOS paper and earlier papers, and you know where they're kind of going. And they did add something about exokernel a little bit, but the logistics of it is you work till the end, and you don't know exactly what your competitors are doing. Once the paper is accepted, once everything is over, you exchange your papers, but till then it doesn't happen. So you can't hold it against them that another paper in the same conference in the same section is not referring. So exokernel did not refer to this work either, right? I mean, so it's fair, right? Because logistically you can't do anything about it, right? But I'm sure when the presentation was going on, they might have been on the same session, so they would have had to chat with each other to make sure that one person is not making claims and the other person is going to disprove or what have you, right? So as you can imagine, this is a time when people are debating what should happen, right? What should happen in the operating systems and stuff. And one of the comments that I saw people make was they haven't seen it in commercial operating systems, right? Commercial operating systems don't seem to have this stuff. And that UW seems to have, University of Washington seems to not do much work on this stuff, right? The second component is not true. They didn't work on spin. They worked on something else. But, they worked on another project called Nux, which unfortunately we're not reading because I think we have too much of these kind of these papers. But that's the excellent paper that came out in 2002, I believe, which talks about these issues. So the ideas didn't kind of go away, but they're kind of working with different stuff, right? But the one thing to remember in all this stuff is they're not commercial products. I mean, this should be pretty obvious to you guys, maybe not now, but when you graduate, right? When you graduate, you want to be known for something. You don't want to be known as the plus guy, right? So if you did something fantastic, you don't want the person who comes behind you to do whatever you did plus and whatever kind of stuff, right? You want to make your own name. You don't want to make your own name. So you don't want to say, he did spin, and he extended spin to use model of 4, and he extended it to run on x86. I extended it to run on blah. And my goal, you know what I mean? So you get all the credit. So all the credit kind of flows back to him to show that this system is like the wonderful system. And all of you basically are helping him, right? Which is not a good career move, right? So you have to forgive people for kind of making it look different. So the Nux paper wouldn't sound like spin plus kind of thing, right? So that concerns you need to kind of avoid. But I think they're trying to solve the same kind of problem as exokernel, right? And I think your answer for the last homework assignment is a lot more applicable here, right? So what are they trying to do? What is the problem that they're trying to address here? Huh? So is it the same as exokernel? Is it like two exokernel papers together, or what? What is the problem that they're trying to address? Yeah.
They want to provide some sort of specialized services to certain applications.
Mm-hmm.
And they don't really want to do it in the same way as an exokernel. They want to have a kind of traditional operating system that allows these modules, whatever you want to call them, to be programmed individually and loaded in for certain.
So they want to solve the same problem as exokernel, right? So they want to make it extensible, right? And they want good performance too, right? So the difference is they have nothing against the operating system size per se, right? They want to load stuff into the kernel to make it do stuff. Why do they want to do that? Why load it to the kernel and not?
They feel it would be faster.
Yeah, so they try to achieve performance by moving stuff into the kernel, whereas exokernel would argue that they make it faster by moving everything out of the kernel, right? So exokernel would claim that they really want the maximum performance, right? Like what these guys would want too, right? So I think both their goals are similar. Both of them want to be able to extend it. Both of them want to get good performance, but the way they address it is different, right? So exokernel, you push everything out of the kernel, right? So if you have a program and it has to do X amount of work, you move as much of it outside the kernel such that you don't cross the kernel boundary often, right? So you want to move all the processing outside the kernel, and the hope is there's only very little that needs to happen inside the kernel. So you need to cross the kernel the least amount of time. They do the exact opposite. They move everything inside the kernel, so you still reduce the amount of kernel switches, because essentially your program runs inside the kernel, and all you have is this little same amount of context switch as what exokernel would do, except it happens to be inside the kernel, right? And their key is, if inside the kernel, your performance is great because now you basically do a procedure call. You're not doing a protection boundary change because you're inside the kernel. So you should be able to make a call to any of the services inside the kernel, right? And the flip side is, I printed out the slides from these. They have this particular graph, right? This is in their presentation. They made the presentation online, so you can take a look at it. So the idea is extensibility. You want to be able to extend the stuff, which is sort of what exokernel wanted to do, and you have performance and you have safety on one corner, right? So their argument is Mark is extensible and safe, but not good performance because you have to do a lot of this crossing between the kernel and the application. Unix has good safety and performance and doesn't have good extensibility. We'll get back to what that means a little bit. And DOS, which is not really operating system, so it has excellent performance because you can do whatever. You can extend it because it doesn't really prevent you from doing anything. So you can do whatever you want, but of course there's no safety because it doesn't really protect you against anything, right? So this is the Unix that they're talking about back then, where you cannot extend it because that's you had the Unix or operating system which is not extensible, right? Is that true for modern operating systems, modern Unix? Is modern Unix here or somewhere in the middle? Modern Unix or modern Windows or modern any operating system you can think of, right? All the three major operating systems, are they in this scheme, are they extensible or not? You would know the answer to this because you've probably seen the effects of this, right? I think you used the word too. Are modern operating systems extensible?
Yes.
How?
Within bounds by using kernel modules.
Yeah, use kernel modules, right? Kernel modules are DLLs or kernel load libraries or what have you, right? So back then, kernels Unix did not do it, but all your current operating systems do that, right? So one of the things that, I don't know if they picked it up from Spin, but that sort of permeates around the system, right? So basically, you can load anything into the kernel, right? You can load a module or a DLL or what have you. Typically for device drivers or file systems or what have you, right? There may be some restrictions as opposed to these people, but I think at the high level we can assume that the modules can do anything that Spin can do, right? So if you can do that, where does it move? Where does a modern operating system move? Does it go here? Does it get all of them? Or does it? Do modern operating systems like Unix and Windows or Mac, they're extensible by using modules or DLLs, right? And so do they have all the other features? Do they have safety and performance? They would have performance because they do the same thing as they do, right? So you should be able to make a procedure call inside the kernel. So let's give them performance. Do they have safety? Yeah.
Not really.
They have no safety, right? You would have seen it because most of your blue screen of death is essentially crash inside the module, right? I think it's very rare for you to find some bug in the OS proper. I mean, unless you're running an experimental version of Linux or something, right? But most commercial operating systems that you buy, or most released versions of the kernel, you don't usually see bugs in the kernel proper, right? You see problems in your device drivers or whatever. Device drivers are essentially loaded into the kernel as a module, right? So that's where we went. I mean, since the paper was published, right? Right now you can load anything into the kernel and you get good performance and good extensibility, right? And we use that pretty much every day because most of us extend it in like a lot of different ways, right? So this work is a lot more relevant now than you may realize, right? Because this approach is sort of what we're doing without the notion of safety, right? So there's subsequent papers which we're not going to read because we don't have time. If you have time, you should look at the paper called Nux. It tells you how to load drivers securely I think they work on Linux, right? So that's a good paper to look at and how to do this stuff, right? So going back to this paper, right? So compared to modern operating system, they can do all the stuff, except they can't do the safety part, right? And this paper claims that they can do the safety part, right? And the claim to safety is through Modular 3, right? And many of you didn't believe that Modular can do what is promised, right? How many of you believe that Modular? So essentially, their claim to fame is you need to load something into the kernel, and we know how to do that from our perspective because that's what modules tend to do. And then you get better performance because you're inside the kernel boundary, so you can access whatever you want. Now the only thing we don't know is safety, and they basically say we have nothing really for safety, except we use Modular 3, right? So what does Modular 3 do that they claim is useful for them? They claim it has good performance, right? They said in the end that they were concerned that whether the performance would be good enough, and they said performance was good enough. And all these programmers were C programmers. All the developers were C developers. So their argument is we could learn Modular 3. It was not that hard to work with, right? I think there's some confusion on what it can support and what it doesn't support, right? So what do you think it supports? What are the things about Modular 3 which?
I think the biggest thing they used was the fact that when you have separate modules, you can't have just sort of arbitrary shared variables.
Mm-hmm.
That everything external to a module has to be explicitly defined via an interface.
Mm-hmm.
So it keeps everything encapsulated.
Mm-hmm. Yeah, so anything inside your module, you cannot access to it. And actually, they actually had a better picture, which I didn't cut and paste, but. So they had one of this graph, right? So if you load 2 extensions into the kernel, right, and if you expose only these particular mechanisms, then only you can access those. You cannot access something that is not reported global, right? So that seems like a pretty trivial programming language concept, right? Even with C, you're not supposed to do that, right? So suppose I wrote a function called, func1. Right, or j or whatever, right? I can't access this integer, and I can't, this one cannot access this one, right? So what's the big deal here? I mean, you can't say somehow I want func1.i, right? I can't get this variable, right? So why Modular 3? I mean, I can use C to get the same thing, right?
Module 3 also checks pointer dereferences to make sure that you're dereferencing the proper.
Yeah, the problem is pointers, right? The problem is pointers, right? Because the C does not let you look at those, right? But I can look at my stack, right? I can look at my stack by looking at the address of j. I mean, if you want to write dirty but nice code, you look at the address of j, then you know what your stack variable is, right? Then you walk the stack. You go back to the stack, so you know exactly where things are. Then you can, with trial and error, or just going through the stuff enough times, you know where things are, because everything is in the memory, right? I mean, all the system things things are in memory. The only way you protect stuff from not being able to see is to use virtual memory, right? So if you use VM to say this one is not read, let's say you have read at X bits, right? If I change it to not read write in X bits, right? Then I can protect it, because whatever you do, this will create some kind of fault that the OS can capture, right? If you don't do that, they all will write within the same address space. They all have the same protection. The stuff which gives you performance is what kicks in here. So if I can somehow find what this address is by going through some stack, right? Then I can get access to this variable, because I can find the address, right? I do something to find the address. Once I get the address, I can say j equals star I, right? Because I'm dereferencing through a pointer, right? I'm dereferencing something randomly created. I randomly found out this thing, not through the program, but somehow. I walk through a stack or whatever. And then I'm able to dereference it to find what the variable is. So I'm able to get to this. Either C does not allow you to do that. I can do that because C does not check for dereferencing, right? You can get the pointer to do whatever you want. That you can't do with modular, right? It keeps track of what the variables are, what you have. You can't just randomly take a address and then change it to whatever you want. It gives you the power to indirect through pointers, right? I think it does give you the power to indirect through pointers, but not necessarily. But it statically checks it, so you cannot do what you're not supposed to do. You can only do stuff that you're supposed to do, right? How many of you are familiar with Java? How does this relate to what Java does? Is it similar? Is it? Did it ring a bell? I mean, does it feel like Java? Does it? What's the difference between Modular 3 and Java from your understanding? Java 3 has other aspects, right? It runs on a JVM. It runs on a virtual machine, so it can be ported to any machines. Ignore that part, right? If you consider a program in terms of protection and stuff, is this similar to what sort of Java does? Does Java let you look at this stuff through pointers or what have you?
No.
Does Java support pointers?
Probably not. I don't think so.
What?
Depends on your definition of a pointer, but not really.
Java protects something by getting rid of some of the pointer stuff, right? So when I look at Modular 3, I think a lot more of Java rather than C, right? It's more like Java, except it has better performance. Except it lets you have pointers, except it lets you get better performance than what Java does. But it's in the same family of programming languages, right? I mean, it does let you some things, right? Modular 3 does other stuff that they don't actually talk about in this paper, right? Modular 3 does garbage collection, right? Which, if you talk to any of these people who in this project or anything, human beings should not be doing malloc and free, right? I mean, they think that memory management should be left to the operating system or the system somewhere, right? You should be able to write code which is garbage collected, right? How many of you use a program language which does garbage collection for you? What language?
Java.
Java, okay.
Perl sort of does.
What does? Okay.
Lisp. Lisp.
Yeah, Lisp does, right? So people who come from that aspects, they don't want to be able to like allocate data structures and deallocate and all those things. They just want it to be managed by the system, right? And one of the problems with the management is if it deallocates, something may be stuck in the buffer, right? And this one takes care of it too. So if I allocate something, use it for something, and the system recovers it, then the new process cannot find out what was stored before it was deallocated, right? So all the memory management is moved into the system, and the system guarantees that you cannot get access to any data that you're not supposed to, right? So all the protection is done either through static checking or some of them through dynamic linking. There's not much checking which goes on at the runtime. I think the array bounce check is runtime, most of the other checking is done statically, right? So when you write the program, it does a static check. So I think one of the problems with Modular 3 compiler is it's very slow, it's humongous. The other problem is it's not portable at all, right? I mean, so we were using it for something else, right? So they ported it to some other architecture, but you had to get the binary because it depended on a whole bunch of stuff. So to compile Modular 3 was a pretty big nightmare, right? But those are logistics, and the world kind of moved on. I don't think Modular 3 is maintained or whatever. But the direction they're going was the Modular 3 compiler is slow, right? It's pretty complex because it's doing all the static checks. But assume that it does all it's supposed to do, right? Then you get the performance because there's not much runtime check being done because all the check is done statically while you're compiling the stuff. And seems like that's the way to go, right? Why should you be doing the checks at runtime when you can do the checks at the compile time, right?
Well, I guess my major question was what prevents you from, okay, now you have a binary that's signed by, or that is compiled by the Modular 3 compiler.
Mm-hmm.
What prevents you from going in and changing something so that it breaks your system, that it breaks something?
You may change the objects.
The binary. Yeah, change the object file
So,
in the way that it...
Okay, so the security claims that they make, you have to read it in the context of a security research, right? Not the operating system research, right? So security stuff, you need to understand that you have to trust something, right? The trusted computing base or whatever, right? So they don't discuss that in this paper because that's kind of orthogonal to this issue, right? You have to trust something, right? So you have to be able to trust this code that you compile, right? It's not modified without your knowledge, right? And they don't say how it is, but we know how to do that. I mean, like, code signing or what have you, right? So other concern you mentioned was, what if somebody hacks a modular compiler to produce code not to check this stuff, right? I think it's far simpler to just change the binary code to something else, right? To change the code to not do some testing. But let's assume that that's not done, right? Because we can have checking and stuff like that. They also agree that there are some things you cannot really trust this stuff, right? All these checkings will make sure that you're not able to access something that you're not supposed to, right? It does not give you the trust stuff. I mean, there's no notion of a trust here, right? You cannot trust this code to do the right thing to the system, right? I can have access to some data, but I can leak it, I can expose it, and all those things. So this is not solving the trust issue. So that's why some of the functions they implemented themselves, because they say you can't really, Modular 3 code does not make it trustworthy. It just means that whatever modules you're loading would be safe. It won't destroy anything else, but it can do untrustworthy things, right? So that's one thing they differentiate, right? So within that context, right? But all they guarantee is if you have some mechanism to protect the binary, right? You should be able to load any binary into the kernel, and it won't do what it's not supposed to do, right? Now, if you wrote a code here which did something bad to the system, is that a bad thing? Intentionally doing something malicious, right? Do you think that this approach will address issue of not the simple stuff, but you intentionally doing something inside the module which is designed to, so denial of service from inside, right?
No.
Right? I think they don't, right? So for example, if you have while one loop inside, right? Modular 3 will not catch that because that's not designed to catch that, right? So those kind of stuff they don't do, right? So they assume that you write good code. So assuming that you're a device writer who writes good code, and you do this unintentionally because of bugs, not because you intentionally try to do something, then this stuff can give you, and if you believe that Modular 3 will indeed do what it has to do, right? And I think it does, right? Because the Modular 3 itself was published in programming language conferences and stuff. So we have to trust that, people who wrote that were fairly smart. So you have to assume that they do what they do. So same like Java, right? We assume that Java does. There must be some bugs somewhere, but we haven't found it yet. So let's assume that it's safe, right? So in that sense, it's safe to that extent, right? But what it gives you is, you as a kernel driver, device driver developer, can develop a driver, right? And you won't unintentionally bring down the system, because anything you do, if you do what your code wants to do, you won't have access to stuff that you shouldn't have access to. You won't be able to modify something you shouldn't have access to, right? So within this context, right? So going back to the notion of the current Unix system, right? Unix are within this way of splitting the stuff, right? I think spin can solve the problem that most modern operating systems face, which is the issue of how do I load a driver where the driver is intentionally trying to do the good stuff, but something's happened, they bring down the whole system. That shouldn't happen here. Do you believe that? We have to assume that no device driver is actually trying to bring down the system, right? Because they don't have any motivation to act like the bad guy. So they're trying to do the good stuff. So they have to buy into the notion of being able to write the code in modular, right? And their argument is it's not that hard. You can pick it up pretty soon. Let's buy that, right? I mean, because it seems like modular 3 is closer to C than Java, right? In some sense. So if you can do that, if you can write a program in modular 3, then you have this added benefit that you get performance, because the modular 3 itself is fairly fast, comparable to, let's say, C. But it has the performance. So any system call, any kernel function is basically a function call, procedure call, not a. You don't have to do a context switch, right? Is this microkernel in any sense? Some of you mentioned that spin would be smaller, right? Spin would be smaller because it provides the basic functionality. Is that true? That does spin only provide the basic functionality for a system? The vanilla spin file system, operating system, right? Is it minimal compared to exokernel, right? Would a vanilla spin operating system be considered monolithic or microkernel or exokernel? Yeah.
I guess monolithic.
Yeah, I think it's monolithic kernel, right? They let you change some functionality by changing the event handler. Everything goes to event handler, right? So you have a default event handler which you change for your particular application to do something else, right? So it actually makes the kernel bigger as you load more stuff. I mean, so they let you load this for different users, right? So potentially your kernel can get bigger and bigger because it's loading more stuff. But it has a base stuff, right? So the basic stuff, I mean, the machine works something, so somebody provides the basic stuff, right? So it's actually more similar to monolithic kernel, yeah.
The way I understood it, maybe I'm wrong, is not necessarily as a device driver as in a monolithic kernel one might see it, but as like an application could install drivers itself.
Yeah.
So does that mean that the I guess my question is it's not so much a device driver in the way that we know a device driver as. It's more of a app, because a device driver, the way that I think of it is, I have a video card, I need a driver for my video card, and the system will use that device driver. Whereas in this system, it's going to be the application needs this thread scheduling package, so it's going to install this thread scheduling package for itself. But nobody else can use that thread scheduling package. Or if they did, they would have to install that as well.
They have to load it into their own space, right? So that brings up the issue of what kind of a device you're manipulating, right? So for the thread package, since they're using the same virtual processor or what have you, right? So you can have multiple thread packages which kind of coexist because the spin kernel itself virtualizes the underlying hardware, right? So you don't get to muck with the hardware, right? So you can have multiple applications using the same CPU through different thread package. And if you wanted your thread package, you have to load it in. But you can play the typical OS games to not actually take up too much space, but whatever, right? So you have to load it in, right? But as you pointed out, there are some devices which cannot be shared like that, right? So the graphics card, right? The graphics card, it may not be possible for you to load a driver which gives you complete control to you and have two different processes load different graphics card, right? So, but actually they do write application which solves that problem, right? So how do you do that? The video program, the video player program, right? It actually decodes the video and gets access to the device driver, right? You remember how they did that? I think they go through the frame buffer. The video program, so you load the video program into the kernel, which does something to the video, and instead of showing it on the screen, it writes it to the frame buffer, right? So it's one level of indirection. So you don't actually get control to the hardware. You don't actually control the hardware. Rather, the hardware is exported as a frame buffer. So all these things can write into the frame buffer. So you can have multiple stuff do that, right? So for devices which cannot be virtualized like that, I don't think you can use spin. But if you can virtualize it a little bit, then you can potentially have two different applications using two different drivers, kind of thing, right?
If you allow an application to write directly to the frame buffer, what makes them play nice?
Do they address that issue? Is that part of their? Yes, that's the excellent question, right? So if you let's say your frame buffer this is what your screen frame buffer is, and you want application 1 to write here, you want application 2 to write here, right?
I mean, even in a more complicated case where you have two windows that are over top of one, not necessarily over top, but kind of
Move on top.
yeah, just like a little bit overlap.
Mm-hmm.
I mean, one of them has to know that it's on top, so one of them has to have focus.
How many of you return graphics code? So how do you do that in graphics when you have two windows which are going over top of each other?
Well, you'd write the bottom one first, right? You write the bottom one to the frame buffer first, and then write the top one over top.
Or you can do the processing to get rid of where the overlap is, right? But I forget what this alpha channel coding or something, right? To look at the stuff, right? But one way to do that is, no, I don't know what they do actually. So one way that programs typically do is they have a notion of a window, right? You write into a pix map, right? You write into a pix representation of this windows given to you, so you get to write into this, and somebody gets to write into this. When it goes over, the X kernel will tell you that you're overlapping over here, and in this simple case, it's trivial because it basically has to not show this pix map, but show whatever is from here, right? So you as application get to write into this bunch of array. This other application gets in a bunch of array. So when you move, actually, the applications don't know that they're being overlapped, right? You can look at the events. Within X you can say I want to look at that event, and you can do something about it. But you don't have to. The default handler would say you just keep filling this one, and I'll do the stuff, right?
So really, you're not getting the entire frame buffer. You're getting.
Oh, that's for X. That's for X Windows,
Oh,
right? That's what X Windows does in the case, right? So what should happen here, right? Should you get, so when they say you get right the device driver, right? Should you get access to something which is already virtualized, meaning like you have now a concept called window, right? If you write in X Windows or whatever, you have this window, right? And Windows typically has little buttons and stuff on this. So you get the widget window, right? Should you be able to control just that, or would you want to get the whole frame buffer where you can do whatever you want, right? Meaning like then you can have a window. So this is what I'm talking about, right? So if you look at this as a window, right? This is not really a window because it doesn't follow the typical XP stuff. Whereas this is the typical XP stuff, right? You have all these things, and I forget what they're called, right? But those this stuff to close the window and open the window and all those things. So it has a notion of a window which is more of a XP, or Vista style of window. Whereas when you're doing a slideshow, right, I want it to have access to the complete frame buffer. It violates all the stuff. I mean, there's none of the stuff, right? So I can do whatever I want. I can draw graphs. I can do videos and stuff like that, right? That's the power I want, right? I don't have to. So if I want to play video movie or something, I want this not to have access to the other window stuff. I want to have the direct access to the buffer, right? So what I really want is not to do what X Windows kind of stuff does, but I want to be able to get access to the frame buffer and do what I want, which is what I think they do in this paper, right? But they don't exactly explain how you protect against that, right? Do they try to protect against that? Do they? So let's assume that you get access to the frame buffer, and you are supposed to write here, and somebody is supposed to write here, right? Can this person write here over this with their approach? I don't think they explain that clearly, but let's. Do we believe that they would prevent you from writing into the other person's area? Because you get access to the frame buffer. I think you have to get access to the whole frame buffer, because then only you can do something like a PowerPoint player or something. You do display the things you want, right? But is there a protection which prevents you from mucking with somebody else's stuff? Does that make sense? Yes, that's your question, right?
Yeah, I just don't know the answer.
Yeah, I mean, so, but I'm saying, do you believe that do they believe that they? I don't think they address that, right, in the version. But I'm saying, do you believe that they can address that?
If Modular 3 addresses it, then they can. Otherwise, they can't.
How will Modular 3 address it?
I don't know. I don't know Modular 3, but the Modular 3 seems to address a lot of issues that they have. So
I don't think Modular 3 can address this issue, right? I don't think Modular 3 can address this issue because Modular 3 is a programming language. It can do array bounds check, right? So if you have an array, right, it can say if you access anything here or here, it can catch it. That's easy, right? Every programming language should be able to catch it. C doesn't, which is unfortunate, but that's a trivial thing to catch, right? But what we're asking is, I want this to belong to me, right? It actually is not even that, right? Because the way it's done. So I'm going to say these bands in the memory. These bands belong to these pix map, right? So if I want to say modular 3, can you make sure that if I access something here, if I modify or write something here, you should give me a exception, right? I don't think modular 3 can do that, right? Because if you want to do that, then it slows things down, right? Because you have to do all this checking, right? So modular 3 does not, I don't think it attempts to do that kind of a complex stuff. So you can make it harder and say, suppose I only have access to this weird shape, right? Which translates into something. So you can't do this stuff, right? So I don't think modular 3 will protect you from this stuff, right? Which means that if I give access to you the screen, you could write over everything else, right? Have you seen that behavior before? Yeah.
I mean, in a way, with applications that run in full screen mode.
Yeah, I mean, like right here, right?
I mean,
PowerPoint did not ask I'm running some IE and all those things, right? But just took over, right? And most of your DVD players, when they go to full screen, they just take over the whole screen, right? And most of us like that behavior, right? I mean, it's not like we want the window stuff, right? So it essentially boils down to, at sometimes you don't like it, and sometimes you don't mind, right? If you're running a PowerPoint player and it takes over the whole screen and displays the presentation like this, you're perfectly happy, right? But if you're doing some calculator program and the calculator is showing the results over here on top of something else, you don't like it, you kill the calculator, right? So their approach, I think, is that, right? Which is, they give you the complete power. If you do something which is making the screen annoying, right, then in this case, they would say it'll go through, right? If you try to access something over here, you cannot do that, right? So the trust here, I think, is some of the things they enforce the trust. They don't want you to do the same thing for CPU, right? If I give you a CPU, I don't want to take the CPU away from you. So they kind of prioritize and say, CPU I cannot trust you with doing this stuff. For the screen, they don't explicitly say that, but the assumption is what is the worst thing you can do? You can mess up the screen and it can kill the process, right? So there's a trust throughout the system, right? I think that's one of the things that they don't actually state. I don't think that they state that too highly. But my belief is there's trust throughout the system, right? The way I get power is I let you load something into the kernel, right? Modular 3 gives you some protection, right? You can still mess with the system on things like this, right? Screen is a good example. I'm sure you can do it with other devices. If there are some things which they deem that you should never be able to do that, like the processor, then you cannot load something on top of it. That goes to the kernel, right? Some of the basic services are provided by the kernel. Other stuff, they give you control. With the power that you get to muck with the system in some sense, right? But if your intentions were good, then this is a good approach, right? But that's what we've been doing right now, right? I mean, if this thing bothers you, then all the computers you use right now should bother you, right? I mean, all the computers you load modules, and the modules can do whatever they want. They don't even have the protection that Spin provides. There's no modular 3. I mean, you're loading some code which can do whatever it wants. You trust that the code will do the right thing, right? And if it doesn't, sometimes you get a blue screen of death. I don't worry too much about the blue screen of death, right? That's the extreme case, right? But in the other times, it can do whatever it wants, right? Your wireless car driver can just go around your system, find all the passwords, and ship it to somebody else, and nothing prevents it from doing that, right? How many of you worry about that? When you load a driver, right? When you buy a printer or something, you get a driver and you load it. Do you know what the driver is doing? Driver has access to all the stuff in your system, right? Anything you do with the password and stuff means nothing, because once you go into the kernel, it has access to all the stuff, right? So your driver has complete control over the whole system, right? It can do whatever it wants. It can look at all the stuff it wants, right?
But does like Microsoft, test out the driver and give it like a certification? Because like when you install driver, you start asking for you like if the driver is signed or not.
So what do you? I don't know what exactly Microsoft does, right? So what do you think Microsoft does? Do you think that it checks the code to make sure that it's not doing anything, or do they check to say this code came from provider X? They sign it, right? Microsoft signs it, right? So does the signature mean that Microsoft is saying this driver code came from HP, or is it saying this code came from HP and we verified that it's doing what it's supposed to do?
I mean, they should,
But what do you think?
I mean, I will be, trust the driver that Microsoft, certify over something like, the driver is unsigned, install it.
But I'm saying like for the signed ones, right? What do you guys think is Microsoft really saying?
I wouldn't be surprised if they just checked to see where it came from, because NVIDIA was responsible for like 50% or more of business crashes when it first came out. Mm-hmm. So I can't imagine that Microsoft went through any Q&A on that driver at all, because otherwise they would have seen that it was garbage.
How would you do Q&A for a driver? Unfortunately, I wish we could have seen the Nooks paper, but you should read it. I mean, there's a lot of good papers we don't get a chance to read. And if you're interested in any of this stuff, I think Nooks is a great paper to follow, right? How would they do it?
The same way I would be testing for anything, really. You'd either have access to the source or not, and if you don't have access to the source, you have to try to stress test it in any way that you see might cause problems. So one of the lines of research, Dawson Engler, right? You guys remember Dawson Engler, right? Who's Dawson?
Exokernel?
Yeah, exokernel guy, right? So he went on to Stanford, right? And essentially his career was in fixing bugs, right? Unfortunately we don't read his papers either, right? But most of them are in looking at kernel bugs, right? Kernel bugs and writing code and everything. And he formed a company, and that's been his the stuff for the last 10 or 15 years, right? So essentially, that's what you want to do, like find automatic bugs and stuff, right? And it's very, very hard, even for the company which has access to the source code and stuff, right? When you move it to another third party like Microsoft, even if you give the source code, right? Analyzing the source code for all possible errors and making sure that you're not causing any bugs is very hard, yeah.
I know that, like for big company like Creative or NVIDIA, Microsoft actually have like people working with the driver developer team, you know. So I mean they have to, because I mean creative need to know, you know, the API underneath Windows to write a driver. So I mean.
No, I agree that they should do that. I'm not saying that. I'm saying all the companies in good faith,
I mean,
right?
It's impractical to do it for every single driver, like because you have like 1,000, 10,000, 100,000, manufacturers for star card and video cards.
I think that's the truth, right? I mean, all the companies involved want to do the right stuff, right? Microsoft wants to do the right stuff because they have no motivation for you to destroy Vista. All the companies, right? I mean, I think you don't just you don't get Microsoft to sign it unless you establish some relationship with them,
and
right?
you have to pay Microsoft to do that also. So I mean, for a smaller company, they cannot afford, to get their driver signed.
Yeah, so there is some incentives in to make sure that people are trusted and all those things, right?
I mean, look at back, like maybe like 20 and 30 years ago, we don't have, a lot of, manufacturers. So I mean, all of them can sit down and then, decide on one type of standard they can follow. But I mean, it's wide open right now, and you cannot have that kind of agreement upon.
What do you mean by a standard? In what sense?
Like we have IEEE, right? Which is we have the standard for like USB 2.0. But I'm not sure that if all the hardware companies follow the same footprint on.
Okay, let's start with the software companies, right? I think that's a good goal, right? Standardized stuff so everyone knows what's going on, right? So presumably, if you're running USB hardware stuff, you can go and buy the standard, and presumably all the hardware will have to follow that model, right? Do you think it's possible in software? I think that's one of the things that people would love to have, right? Be able to kind of know what exactly is Microsoft supposed to do, right? There are business reasons why they don't do that, right? Microsoft is an ad hoc standard, right? They don't actually say this is all the stuff that we want to do, we like to do, right? No, people love to get that, right? People love to get to the stage where it's all standardized, so we can know exactly what things should happen, right? But I don't think we are quite there yet, right? I think one of the nice things about this particular paper is they give you some support within the system, right? So I think right now the model is you sort of trust Microsoft, right? You have to trust Microsoft, right? I never understood why when you install, they ask you to trust Microsoft in some context. They say like, do you want to trust Microsoft, right? And the question is, if you don't trust Microsoft, then why are you running Vista? I mean, you have to trust something, right? So you trust Microsoft, you trust that Microsoft does a good job of bringing these people, trusting those things, right? So even if you have all the trust and people are doing the right thing, there's nothing programmatically which prevents them from doing something malicious, right? Either malicious or unintentionally bad. Unintentionally bad, you sometimes see it as a blue screen of death. Other times it may corrupt something that you don't notice, you don't know kind of stuff, right? I would think that if you use Spin with the model that we have, you will produce better, robust software than what you do right now. If you use Modular 3, but have all the other stuff, you still have it signed by Microsoft and you still have all the stuff, you will reduce many of the bugs that you see in module-based systems.
Does it mean that everybody has to use the same programming languages? Because I mean, they say that you have to use Modular 3 to compile the program, even though to run it in Spin.
So how do you do it right now for Microsoft? I don't know the answer because I'm not the one.
I would say for the driver, I think they need to use assembly code to write.
Actually, I think Modular 3 will lets you do assembly code, but there will be restrictions, right? There will be restrictions on what you can address within the assembly code if they could, right?
I think Windows drivers are C and C++.
What?
I said C and C++.
Okay.
I mean, at least support for drivers in Windows kernel.
But his point is some of the things has to be in assembly, right?
Yeah.
Yeah, so the way you develop code is you have to have something in assembly, right? Or assembly in C++ or C assembly, which is still the same, right? And then you have the C stuff, right? So hopefully if you're writing a driver, you keep those stuff to a minimum, right? I mean, the actual assembly code that you need to directly manipulate is hopefully small. And then you have a larger piece of C++, right? C++ code, right? I would be worried if they wrote the whole driver in assembly code because it produces too much bugs, right? So that's a good point, right? So you may have to allow this modular or whatever language you are having to have access to assembly language, which pretty much means that code can do whatever it wants, right? Because the protection boundaries, I mean, modular cannot possibly check those code segments, right? Is that the I think there are people thinking of ways to solve those kind of issues, but that's a good point, right? The assembly language is a problem, right? You mentioned multiple programming languages, right? Is that really true? Do developers want access to other languages, other high-level languages, right? How many of them are developing in BASIC or C or something like that, right? How bad is forcing you to work in Modular 3 if Modular 3, let's say, is fairly decent? So Modular 3 is going to be annoying for two things. One is it's going to be annoying because you need to learn a new programming language, which you never knew before, and you have to use it, right? That's annoyance, right? The other annoyance is Modular 3 is not letting you do something that you want to do, right? Either because that's something that helps your program, or because that's something that you always use. Like, so in this case, you wanted to get access to this stuff because you don't want to go through this abstraction of like exposing this stuff because you just want this quick stuff, right? So Modular 3 is going to prevent you from doing stuff that you shouldn't be doing. Modular 3 is going to be prevent you from doing something that that you want to do and it should be allowed to do, right? The part about not letting you do something that you want to do, right, could be fixed, right? There are some things that Modular 3 is explicitly preventing you from doing it because it considers it to be unsafe, right? I would argue that those things you have to live with because that's the whole premise of this stuff, right? If you use those stuff, if you say there is no way, whatever you do with the stack, that you will be able to access this variable from that, right? To get safety. I mean, they achieve safety by restricting you from doing this stuff, right? So if you're used to like having unfettered access to the whole operating system, you would be unhappy. But their argument, I think, like they're trying to make at the end was the language is powerful enough that it can do most of the other stuff that you would want to do with it. It lets you gives you pointers and all those things, so you should be okay. I don't think they would be able to do assembly language fully, right? But other than that, what is wrong with forcing people to go into one programming language if it will buy you stuff? And Nux takes a different approach. Actually, Nux is a little better. They protect what it's able to do. But I think Spin is more general, right? Does an exokernel use something like this within exokernel too? Don't they? If you load some piece of code inside exokernel, you use the programming language constructs to give protection, right? They don't expand more on that because that's not their specialty, right? Right? The bottom line is this line of research, there's a lot of people who are working along this line says if you can constrain the language to not let you do certain stuff, right? Then if you can solve many of your problems, maybe you have to look at it. So there's like a lot of push to have Java operating system, right? Operating systems written in Java, right? Which would be taking it one more step further, I would think, right? In terms of restricting what you can do and all those things, right? You don't seem convinced on that that's a way to go, right?
I just have another question. So,
yeah.
I mean, I think Spin is good if you have like a single user and a single application.
Mm-hmm.
So I mean, the application can modify the behavior of the OS using extension. But if you have like multiple users and multiple applications, for example, like each application has its own thread scheduler.
Mm-hmm.
I mean, if you run thread like in user space, okay.
Mm-hmm.
But if you have like a kernel level thread,
Mm-hmm.
then you know which scheduler you use for the whole system. When you have like multiple users and multiple applications.
So your point is, I'm going to paraphrase it to make it more general, right? So you have something here, this is user level, right? There's a process 1, there's a process 2, right? And this wants a thread library 1, and this wants a thread library 2, right? And you're worried, how do they interact, right? So if you do this with exokernel, this will be here. If you do it with spin, it will be here, right?
Yes.
So is a question related to spin or the notion of these two thread packages? Yeah, actually, do you have something?
Well, the way I understood it is the kernel scheduler would pick one of the two.
Mm-hmm.
If there's only one CPU, the kernel scheduler would say, okay, it's application 1's turn, so it says application 1 thread scheduler, you pick a thread.
Mm-hmm.
And then it gets preempted, and then this kernel's like, well, okay, now it's application 2's turn, so then it talks to application 2's thread scheduler, and then that's it.
Yeah, so I think basically there's a CPU scheduler here, right? I'm saying the difference between exokernel and this approach is exokernel is here. The application level stuff is in the application level, and in spin it's inside the kernel, but it's still built on top of this stuff, right? So it is a good question to figure out what really happens to these systems, right? So if this one wants high throughput and if this one wants high access latency or whatever, what do the combination of this and this get, right? That's a good question. We don't know the answer for, right? But in terms of functionality, I don't think that exokernels and this one would be all that different, right? All they do is basically move this logic from somewhere else to somewhere else, right? They move it from the exokernel is in application space, and here they move it inside, right? But the larger question of what happens if you completely customize the system where each user is running their own stuff, right? Even though they're running their own stuff, what is the global behavior across the whole system, right? Does it make sense? That goes back to the root of all this stuff, right? You want complete customizability, but if you have two different goals for the customizability, how do you, I mean, you can do both of them at the same time, but what's the combined behavior, right? I'm sure you're not going to get as good a performance as if you're the only one, right? I think Jerry pointed it out too, right? You can have a lot of applications. So in the worst case, right, if every application has its own thread scheduler, right? Then I don't know what will happen if you let it do. I mean, it'll do what they're supposed to do. Each one will do what they're supposed to do. But the interference among all of them would mean that none of them would actually be what you thought they would be, right? But in terms of, so that's the general problem with all this stuff. If you want to customize it, then the customized behavior, the sum total of all the customized behavior may not be what you wanted, right? But in terms of comparing this with the exokernel approach, I think they would behave like the same thing from a user perspective. That's the notion of where you write the code. I mean, in exokernel you write it and then you put it in your library. Here you write it in modular 3 and then you shove it into the kernel, right?
So in exokernel you can share like thread library, right? But can you share the thread model? Like
you have to load it for each application.
Copy a bit, right?
No, it doesn't have to be 2 copies. I mean, it has to be loaded, right? And you remember all the OS issues of how to share pages, right? I mean, they don't have to be physically copied twice, right? We do this trick all the time in virtual memory, right? Essentially, all you have to do is like this process will map these pages, this process will map these pages, and since these libraries are read only, right? Code is read only, right? So you can share it among as many applications as possible in terms of space, right? Because you cannot share your thread modules stack, right? Because that's the different per each of them. But there's no reason why you should copy the whole stuff over, right? Their particular implementation may not implement that. I don't know what exactly they do because it's not a production system, right? But we've been doing this in the application space all the time. If you run Word and PowerPoint and something else from Microsoft, they probably all share the libraries, right? So the library code they are loaded into each process, but they're shared because they are read-only, right? So you'll do the same thing, right? So that's the efficient application, the stuff that we know how to do that. So let's assume that they do that, right? There will be overhead, right? I mean, so I think somebody pointed out that there will be overhead compared to the array bounce check may add some overhead, right? Actually, I think like most of if you write commercial software, you don't even if you write in C, right? Many of the commercial software, they add libraries which do array bounce check for you, right? I mean, you can link with these. There are specialized providers which sell memory allocator libraries, which does some of the checking for you. And the assumption here is yes, there's a little bit overhead, but it's okay because the benefits of doing array checks is good, right? So in some sense, the argument is, do we need to go for the last bit of performance, or can we sacrifice something to get this benefit, right? The way you can do right now is I can write the whole darn driver in assembly code, right, using like no software engineering concepts or whatever. And with this approach, there'll be some things you can't do because of the benefits you get, and the system is definitely going to be slower than if you use assembly code. Is that a penalty that is worth paying? If in return what you get is your machine, because I argue that blue screen of death is nobody's intention to create, right? Blue screen of death is when your code does stuff that messes up something else, right? Yeah.
It brings us back to what we were talking about last time when talking about scheduling processes and having, the cost of disk versus the cost of CPU time versus the cost of network time. It's the same thing. What is the performance penalty that you pay versus the advantages that you get? And it's a function that has different values based on who you are. So.
But I think the value is something that we all can appreciate because most of you, how many of you seen blue screen of death in Windows, right? How many of you seen blue screen of death in Mac? It's not blue, right? It's gray screen of death, right? How many of you seen like whatever color screen of death in Linux, right? It happens in all the systems, right? It doesn't happen all the time. It happens rarely, kind of stuff, right? If it happens all the time, it's very easy to solve, but it happens rarely enough, right? I had a problem with my laptop that is a Mac, and there's some problem with the SMC driver, right? The power controller driver. So if I close the laptop, at certain times it code dumps, right? It's been doing that since 10.4, and it's been now at 10.5.5. And every time I sincerely send the bug report to Apple, but nothing seems to get fixed, right? There's something wrong with the driver, which seems to be surviving major revisions in OS and minor revisions in OS. It keeps going, right? So you see those stuff. I mean, this code was actually written by Apple because it's in com.apple.smc something. So it's written by Apple, right? So you would think that they know how to fix it, and apparently, whatever, right? For whatever reason, it keeps failing, right? If you can do something to solve that, right? Using programming language stuff. So the yeah.
Well, the point is that how much of an inconvenience is that for you? And then is it more of an inconvenience to have that to happen every once in a while, or to have your system always run 1/100th as fast as it does?
Oh, that's clearly a strawman argument, right? 1/100th of a time.
Pick a number. So that's kind of what I was talking about. You need to know exactly what the performance penalty is and what the utility benefit is. And if the utility benefit does not outweigh the performance.
So they do performance, right?
Right.
So what is the verdict from their performance stuff? Is it slower than?
It's good.
It's actually better, right?
Yeah.
Do you believe that it'll always be better?
Well, I mean, it's better than Mach, and it's better than the deck one, but we don't know how it compares to other things such as
Ultrix. You should consider with Ultrix, right? OSF 1 is a microkernel.
Right, but we don't know how it compares with, say, exokernel. Because I don't know if they I don't remember what the specific values.
Yeah, I think it's fairer to compare this with Ultrix, right? Which is the monolithic kernel from DEC, which is completely optimized to provide good services, right?